So in this video, I'm going to be reading Peter Sykes, as I said in the previous video. So, factors influencing electron availability. In the light of what has been said, any factor that influence the relative availability of the electron density, in particular bonds or a particular atoms in a compound, might be expected to affect very considerably its reactivity towards a particular reagent. A position of high electron availability will be attacked with difficulty. With all, by example, for let's take an OH minus, whereas a position of low electron availability is likely to be attacked with ease, right? Inductive effect. In a covalent single bond, whereas between unlike atoms, right, there's an electronegativity difference. So the pi bond is never shared equally between the two atoms. It tends to be attracted a little more towards the more electronegative atom. As you can see here, Cl is more negative, so it'll make a del minus charge here and del plus here. And a carbon atom bonded to chlorine is itself attached to further carbon atoms. The effect can be transmitted further. The effect of inductive decreases with increasing distance, and normally it's neglected after like the third carbon, and it decreases as you move away, right? Like there'll be a del plus here, then del plus. That means it's getting even more smaller. After that, we can just neglect after third. The effect of chlorine's atoms partial appropriation of the electrons of the carbon chlorine bond is to leave C1 slightly electron deficient, right? This it seeks to rectify by in turn appropriating slightly more than its share of the electron of the sigma bond, joining it to C2, and so on down the chain. The effect of C1 on C2 is less than the effect of Cl on C1, like I said. And transmission quickly dies away in the saturation chain, usually being too small or noticeable beyond C2, or like as I said C3, you can just neglect after that. These influences of the electron distribution in sigma bonds are known as inductive effect. In addition to any inductive effect, operating through the bonds in a compound, an essentially analogous effect can operate either through the space surrounding the molecule or in a solution via the molecules of solvent that surround it. In many cases, however, it is not possible to distinguish between the operation of an inductive effect as such and this closely similar and parallel field effect. Subsequently, reference to an inductive effect will therefore normally be taken to include any such field effect. Most atoms and groups attached to carbon exert such inductive effects in the same direction as chlorine. They are the electron withdrawing groups. Owing to their being more electronegative than carbon, the major exception being alkyl groups, which are electron donating groups. Through the effect is quantitatively more small, it is responsible for the increase in basicity. That results when one of the hydrogen atom of ammonia is replaced by an alkyl group, in part at any rate for the radius substitution of the aromatic particles in the methyl benzene than in benzene itself. All inductive effects are permanent polarizations. It's a permanent effect in the ground state of a molecule and are therefore manifested in its physical properties. For example, its dipole moment. Now, coming on to mesomeric effect. These are essentially electron redistributions that can take place in unsaturated means double bond, triple bond, and especially in conjugated systems via their pi orbitals. An example of the carbonyl compound whose properties are not accounted for entirely satisfactorily by the classical formulation, nor by extreme dipole obtained by shift of pi electrons. So just shifting it plus here, minus here. The actual structure is somewhere in between IE21AB, which is the resonance hybrid, a hybrid of which are canonical forms. There would also be an inductive effect as shown, but this will be much smaller than the mesomeric effect. Obviously, resonance will be dominating over, what do you say, inductive effect. As sigma electrons are much less polarizable and hence less readily shifted than pi electrons. In if the carbonyl group is conjugated with double bond C, the above polarization can be transmitted further via the pi electrons. Delocalization takes place so that an electron deficient atom results at C3 as well as C1. You can just see over here. The difference between the transmission via a conjugated system and the inductive effect in a saturated system is that here the effect suffers much less diminution by its transmission and the polarity at adjacent carbon atoms alternates. A stabilization that can result by delocalization of a positive or negative charge in an ion via its pi orbitals can be a potent feature in making the formation of the ion possible in the first place. It is, for instance, the stabilization of the phenoxide anion by delocalization of its charge via the delocalized pi orbitals of the nucleus that is largely responsible for the acidity of phenol. See, I told you, right? OH goes when you dissolve the H goes, so you get a minus there, and it'll go in orthopara. Right? So charge and will be correspondingly less affected in the stabilization of phenoxide ion, which does not. Mesomeric, like inductive effect, are permanent polarizations in the ground state of a molecule and are therefore manifested in the physical properties of the compounds in which they can occur. The essential difference between the inductive and mesomeric effect is that while inductive effect can operate in both saturated and unsaturated compounds, mesomeric effect can only occur in unsaturated. The former involves the electrons in pi bonds, the latter those in pi bonds and orbitals. Yeah. Inductive effects are transmitted over and only quite short distances, yeah, in saturated chains before dying away after like the third couple, as I said. Whereas mesomeric effect may be transmitted from one end to other of quite large molecule provided its conjugation is present. You keep on doing it, checking all the resonance structure. It's like as they proceed, you can just keep doing it. Coming on to hyperconjugation. See here, what we check in hyperconjugation is alpha carbon, and in that alpha carbon check alpha hydrogen. This alpha hydrogen increase stability increases, right? Whenever the alkyl is attached to an unsaid double bond or a benzene nucleus, the order is found to be disturbed. In the case of some conjugated systems, actually reversed. It thus appears that alkyl groups are capable in these circumstances of giving rise to electron release by a mechanism different from the inductive effect. This has been explained as proceeding to an extension of conjugative or mesomeric effect. Delocalization takes place in the following way. This H, alpha H, you take out, you get an H plus here. Same way you can do it for this, and that. This is called hyperconjugation and has been used successfully to explain a number of otherwise unconnected phenomena. It should be emphasized that it is not suggested that a proton actually becomes free. It's not suggested that this just becomes free like that. If it is moved from its original positions, one of the conditions necessary for delocalization to occur would be controverted. The reversal of the following expected order of electron donating to this could be explained on the basis of hyperconjugation, being dependent on the presence of hydrogen on the carbon atoms alpha to the unsaturated system. So clearly, the maximum with CH3 and non-examined Me3C, right? So like when it's joined there to the carbon, like this is the alpha carbons. You can see over here, this is the alpha carbon. So it's like increasing like this. Here, hence the increased electron donating ability of CH3 groups under these conditions. Hyperconjugation, however, involves C single bond as well as CH bonds. And the differences in relative reactivity observed in a series of compounds may actually result from the operation of solvent as well as hyperconjugative effects. Hyperconjugation has also been invoked to account for the greater thermodynamic stability of alkenes, in which a double bond is not terminal compared with isomeric compounds. You can see here how many are there? 3, 6, 9. How many are there? 3, 5. So 3 plus 2, 5. Yeah, so this is more stable. This results in preferential formation of non-terminal alkenes in reaction which could lead to either these or their terminal isomers, okay, on the introduction of these double bonds. Now moving to steric effects, we have today been discussing factors that may influence the relative availability of electrons in bonds or at particular atoms in a compound, hence affect that compound's reactivity. May be modified or even modified by the influence of steric factors. Thus, effective delocalization via pi electrons can only take place in p or pi orbitals on the atoms involved in the delocalization, can become parallel or fail nearly so. If this is prevented, right, significant overlapping cannot take place, right? And delocalization may be inhibited, okay? Let's take an example of this, right? The NMe2 group in diagram 32, as you can see here, being electron donating group as it has lone pair, reacting as it is resonating with the benzene ring. Obviously, it will be doing ortho, para, ortho, it will be active. As you said, like carbon anion lone pair will be going in ortho, para, ortho with negative charge there. Over here, it activates the nucleus towards attack by diazonium cation, which is pH into plus, towards the para position, which is known as azo coupling. The 2,6-dimethyl derivative shown in 33 is not coupled under these, 33, so when you put Me. Under these conditions, however, despite the fact that the methyl groups that have been introduced are much too far away for their bulk to interfere directly with the attack at the para position, the failure to couple at this position is the fact due to the two methyl groups at the ortho you put interfere slightly with the two methyl groups present on the nitrogen, and so preventing this to lie in the same plane. As you can see over here, As I've told in the basic strength lecture, this ME will make this turn and make the lone pair not go in resonance with this, which makes it lone pair more available, which makes it more basic. As you can see, attached and so pyrimidine lies in the same plane, and so as the benzene nucleus. This means the p orbitals on nitrogen and on the ring carbon atom, which are prevented from becoming parallel, but it has to be parallel, has to be in the same plane for resonance to take place. So it's not possible for resonance to take place. This is called a steric hindrance, right? Okay, so this part I have to read once more. I will be telling it later on. The next lecture is probably going to be GEE ADVANCE PYQs. Okay, thank you.